Hey everybody, before we get started, I want to clear up something, kind of a misconception, I think, in terms of what something, certain labels we assign to our numbers. But let's take a look at the number 49 over 25. Now, a lot of people would shudder at calling this a perfect square. They think it's just reserved for integers, and it is most of the time. But let's not let what we call something rule our thoughts here. Uh, we can write this as 7 over 5 squared, and that makes it a square integer, a square rational number. So if you don't call it perfect. If you want, perfect adds no value, but it is a square rational number, just like perfect does. Is just confused. Perfect square for integer, perfect's pointless. In fact, you can get it confused with perfect numbers. So in any event, this is an example of a squared rational number. Now we're seeking x and y that are non-integer rational numbers. That's what this symbol means, folks. This really means the same thing as q minus z right here. Now you may think that's unnecessary. Maybe it is, but we're looking for a rational number that's not an integer. And most of you probably would say, well, this doesn't look like an integer, whatever, satisfied. And I agree, but I'm just being specific with the instructions, okay? Now, another thing that turns out to be useful right here is you can write this as notice that 73 is a prime number. It has no factors. There's no square divisors. It's a square-free radicand. So you can write it like this, which turns out to be big time useful. And this took a lot of discovery on my part. A plus B times root 73. And again, I was slow on this. It really took quite a bit of time for me to realize how important this was. But right here, a plus b must be equal to 1. Okay. Why are we interested in this? Well, we're trying to write this as the sum of two square roots. So we need to get kind of a handle on how we're going to go about this. So we have a plus b is equal to 1. Simple fact, but it's related to the nature of the solutions. We want the square root of some rational number plus the square root of another rational number to equal this irrational number. All right. Now, so let's go down now. Most of the work has been done already down here. I've just taken the givens here, and I won't say much. Used the information, that was given to us, and I used this algebraic identity, which is quite useful. A plus b quantity squared is equal to a squared plus b squared plus 2ab. That's exactly what's going on here with different names. All right. And then again, using the fact that x plus y is 365 over 9, we get to this stage right here. And this is some arithmetic I didn't show you. We can live without that, right? Okay. Now, so we get to this point right here where 146 over 9, a perfectly valid rational number, is equal to the square root of the product of two rational numbers. Now, I squared away to make it a little bit easier to identify what we're doing right here. If you take a look here, the assignments 4 times 73, okay, 4 times 73, and it's about splitting this up to where you get that sum of 1, okay, over 9, right? Now, yeah, you can see what I've done here. I've taken the entire 4 here, right? All right, and then I've used one of the 73s and one of the 9s. Now, also, just to keep things tidy, we could write this as 73 over 9, right here. And you see, we've maintained all of the factors that are present. It's almost combinatorics. You're counting everything. You see how everything got maintained? Both 9s happened down here. The 4 happened, and then the 73s got split apart, okay? But notice that if you assign this to x, okay, if we let this one be x and this one be y, look what happens. Okay, we get the square root of x equals to 2/3, and here's where the 1 is coming in, 2/3 times root 73, right? Isn't that cool? All right. Now there's some other tries. I'm just cutting right to the chase. There's a few other tries, but it's pretty clear you're not going to get the 1 to happen. Okay, now we also get square root of y. Is equal to 1/3, right? And so the sum is certainly 1/3 root 73, excuse me. All right, folks, and so you see how we got this 2/3 plus 1/3 is equal to 1? It's exactly what we needed. And again, if you try other combinations, it doesn't work out, or not any that I found. I think there's only one solution here. So 2/3 plus 1/3 equals to 1, and we found our two solutions. Without even, you don't have to go back and check. You know that it's right because it meets the condition that I wrote right up here, right? It meets this condition right up here. The a plus b has to equal to 1, and you have to have a root 73, and that's guaranteed to be equal, you know, because we're using the rest of the conditions in the problem without you. So some of you may be nervous and want to check this, but you can take this one to be x. So what I have here, folks, is this would be what? 4 times 73 is 292. Isn't it? 4 times 73 is 280 plus 12. That's 292. Okay, so 292 over 9 for x, and then just 73 over 9 for y. And I'm fairly certain these are unique because, again, I didn't show you the trial and error right here. There's other tries other than this. You can split this apart different ways because you got different combinations of exponents to work with, but you'll never get the condition that you need, which is this summation to 1 here. Okay, so these are our answers. What I got. Okay, and again, if you doubt it, but there's not a whole lot of computation going on right here. Okay, when you take the square root of this, you know, you get this. When you take the square root of this, you get this. And when you sum those up, you manifestly get the square root of 73 because it's 2/3 of the square root of 73 times 1/3 of the square root of 73. So again, I thought that was kind of a cool problem. Let me know what you think and if it's worth doing these kind of problems. And I think there's an infinite number of rational. I think it's pretty clear there's an infinite number. I just used 1/3. The solution that I did, well, for this particular constant, I'm not sure. Maybe this is unique, but in general, I think if you don't have a restrictive condition like this, you're going to have an infinite number. If you don't have a restrictive condition like the second condition, you will have an infinite number of rational, non-integer rational solutions. Okay, that would be another video that I could consider doing. But anyway, there you go, folks. 292 over 9 and 73 over 9 is what I got. Okay, thanks for viewing.